Okay, let's move on with the carbon cycle. Remember, these are elemental cycles and we are just looking at carbon. We looked at the flowchart kind of thing here very schematically about the sinks and the sources of CO2. Now I also have been saying that we are increasing greenhouse gases, which means there must be some way that we are measuring the increase in the greenhouse gases. Let's just focus on carbon dioxide here. And we are increasing means what? It has to be compared with something, right? So when you get older, your age is counted from the day you were born to say you are 3 years old, 5 years old, 10 years old, and so on. So there is a way to use the calendar to count your age. Similarly, we need to be able to count the concentration of CO2 in the atmosphere, and because it's in a very small amount, when we say nitrogen is 79% of the concentration of in the air, we know that if we take 1 kilogram of air, there will be 790 grams of nitrogen, let's say. Okay, so the CO2 is so small that we cannot directly say its weight. So what we do is we take 1 million particles of air and we see how many particles are CO2, and this is called parts per million by volume. If you can remember, great. Otherwise, just remember that it's a very tiny amount compared to nitrogen and oxygen, and of course even compared to argon, which is the next biggest gas in the atmosphere. Why are we worried about CO2 so much? Because even though it's in a small quantity, it is trapping the thermal energy that is trying to go out of the earth. If it is not allowed to go out because of this small amount of CO2, for those who are older, this is called a trace gas. Okay, so it's parts per million by volume, affectionately just called ppm, parts per million. By volume is not always mentioned. Okay, so here we are showing the first diagram of how we are measuring CO2. So this is showing CO2 concentration every year from 1956 or so to the present, which is let's say, as I'm recording this is in April 2024. This is data of May 5th 2024. You can go on the web and use this link here. Data is from NOAA. It's being shown on a website called co2.earth. If you don't know how to do that, please use your mother, father, sibling to get it done. So it says new CO2 record high. What do you see here? You see that it's increasing year after year after year. So it is continuing to increase since the time it started to be measured. There was a very smart graduate student called Charles David Keeling in the United States at the Scripps Institute of Oceanography, which is in La Jolla, California. There is California again, the western coast of the US, and La Jolla is in the south of California. And his advisor, Charles Keeling, David Keeling, was doing a PhD, which means a doctoral degree, and his advisor, when you want to do a doctoral degree, there is somebody who is advising you to see how to do your research once the topic of your research is decided. If you don't know what that means, don't worry about it. So the advisor, Roger Revelle, told him, we need to monitor CO2 because we are burning so much fossil fuel and we need to see what's happening to it. The best part about CO2 is it's very inert. It doesn't easily get decomposed or interact with other things. We said photosynthesis takes up CO2 and produces carbohydrates. So that's one way that CO2 is taken out. It can dissolve into the water, ocean, and so on and so forth. But in the atmosphere, once it's been put out there by our breathing, by the vegetation decaying or burning of fossil fuels or cooking at home in some form of smoky thing like wood or coal, then that is going to go into the atmosphere and it will stay there for a long time, which means using the winds we learned about, it can go round and round on the earth. So if you measure at one place, then it gives you a good sense of what is the concentration, what is the parts per million by volume of CO2 across the world. That's how this was done. So David Keeling put one observatory of one instrument to measure CO2 in Mauna Loa. Mauna Loa is in Hawaii, which is part of the US. It's in the western eastern part of the Pacific, approximately in the north, and it's famous, as a very nice warm island, a volcanic island, basically with some active volcanoes still spewing some magma, which people can go and see. Beautiful island, lots of nice beaches and good food and so on. So each year it records CO2 concentration, and every year we can see that it is increasing by 3 or 4 ppm, and if you carefully observe, it is increasing more and more per year. It used to increase by 1 parts per million per year, then it became 2 parts per million per year increase, now it's 3, and now it has become almost 4 parts per million by volume, which means we are burning more and more fossil fuels, we are producing more things in industrial processes, and we are increasing it, and so on. Okay, so we got data from 1950s onwards that is directly being measured. What if we want to figure out where we were when we started the Industrial Revolution? Because remember that I already showed some figures saying we have been warming since the Industrial Revolution, which started actually in the 1700s, and we've been increasing greenhouse gases since that time because of increased coal burning and then petrol and gas, and now we're doing more solar and wind. How do we know before David Keeling started measuring it? There are many ways in which we do it. So you can see that here, this is what Keeling started measuring in the 1950s, and it shows these ups and downs. Here we remove the ups and downs by averaging over the whole year. But the good question for you is, why does it go up and down when you measure every hour, every day? You already learned about photosynthesis, you already looked at how vegetation changes with the ITCZ, sun moving back and forth, and you know that when the winter comes, many trees lose their leaves, and when sun comes back into the northern hemisphere, let's say across the equator, more light becomes available, then photosynthesis begins to pick up again, so a lot of carbon is taken out of the atmosphere by photosynthesis. And when summer is over and fall comes and cold temperatures begin to arrive as sun begins to go south, leaves fall, photosynthesis slows down, and trees begin to emit that CO2 that they had locked up with photosynthesis. So every year it's going up and down with the seasons drawing down. Plants become a sink with photosynthesis during spring and summer, and fall and winter they become a source to the atmosphere. But you can see that it normally comes back, which means there are some year-to-year changes, because if there is more rain, maybe more photosynthesis happens, trees go better. If there is less rain, if there is a drought, or if there is a wildfire, then that year you may have more CO2 coming out of the plants. Okay, it's very simple and looks like I'm speaking fast, but I'm not saying very complicated things. Photosynthesis on a planet, all of Earth, in the northern hemisphere, during the northern hemisphere summer, which we call boreal summer, drives photosynthesis and reduces the CO2 across the globe. And when fall and winter come, photosynthesis reduces in the northern hemisphere winter, fall, and then CO2 is released. So you have, this is called a sawtooth pattern. If you look at the saw carefully, it has these serrated tooth-like features, which is what you are looking at here. So how do we estimate the CO2 before David Keeling started measuring in Mauna Loa? There are various ways. There are ice cores in which CO2 gets trapped, as we will see in a minute in the next slide. There are various other measures that in the lakes, in the oceans, these are called the detective work that we talked about. These are indicators of CO2 from the past, and you see that we don't see the yearly up and down because such a close year to year, day to day measurement is not possible when you go in the past. You can get an evidence of how it was averaged over 1 year or 2 years or 10 years based on what is the source of this measurements or this detective work. If you don't understand, again, depending on your age, you can either go find more on this from my website, from my YouTube channels, or elsewhere to see how that works. But we'll see the glaciers and ice cores in this context, and then we'll come back to it later on when we look at climate change in a more detail. So here is CO2 concentration in parts per million from Mauna Loa, Hawaii. Okay, so going from the Industrial Revolution 1700s or 1750 or so to 2021 or so here. Okay, just 2020, let's say. Okay, so pre-industrial levels of concentrations were 278 parts per million when averaged over the globe. This is what happened when the last ice age ended. During the ice age, remember, CO2 goes down because the vegetation is covered by the ice, oceans are covered by the ice, and so on. So CO2 from the atmosphere is hidden away during the ice age. So it was about 100 ppm lower than this. So it was about 180 ppm during the last ice age, as the ice age began to end around 18,000 years ago and ended by 10,000 years ago, let's say. It was at about 278 ppm till the Industrial Revolution began, because human activity was going on. They were deforesting, they were doing agriculture, they were increasing the number of cattle and so on. So it was slightly increasing, but it was not increasing as fast as it is now. So you can see that after the World War or so, when the industrial activities and population and our lifestyles with lots of energy consumption began to go up, CO2 began to increase very rapidly. Okay, so few things to remember. CO2 is an inert gas and gets mixed around the world. So if you can measure at one place, you get a good sense of what the global concentration is, and this is directly measured at very close time intervals since 1956 or so, when David Keeling started to measure it over Mauna Loa, Hawaii. We can start to derive CO2 concentrations from other evidences from the past. So we are looking here going back to the beginning of the Industrial Revolution. So you want to remember that it was 278 ppm. By 2020 it jumped to 417 ppm, a 50% increase over this period, as you can see here. So you can do, 417 minus 278 divided by 278 or so will tell you how much we increased, but you can see clearly that it is increasing. We'll come back and see something more exciting. We'll see how ice cores are trapping this information of how the atmosphere looks in the past, and how far back can we go with this. We say there are glaciers on Antarctica, there are glaciers on Greenland, there are glaciers on mountains like Himalaya and Andes and other mountains around the world, and all of them are trapping some information of that time. So if you can figure out at what time that information was locked in and what the concentration of CO2 was at that time. So we say here in 1780 the CO2 was here. So you need to time that information and you need to measure the concentration at that time. So you need two pieces of information if you go back. right? So we'll come back and see how that is done. This is really exciting detective work, and this is really important for your future because you're young and the future is yours. And if we keep increasing CO2 the way we are, it can be bad news for you. So you need to understand this as well. Okay, so we'll come back and discuss ice cores and how far back we can go to find past information about CO2 in the atmosphere. Similar evidence also exists for methane, for N2O, and rainfall changes, temperature changes, and so on and so forth, that we'll discuss as we go along. See you in the next podcast then.